Okay, today we're going to talk about the simple Langmuir model and derive the Langmuir isotherm, which is one of the most important ideas in the area of binding. And so we're going to look at this today in the context of adsorption of gas particles onto a surface, but we'll see in subsequent videos that the Langmuir isotherm applies equally well to binding of drugs to receptors or neurotransmitters to ion channels, all sorts of places where we have binding interaction. And it is the first place to start in trying to model that phenomenon theoretically. All right, so for us today, we're going to look in the context of a system that consists of a surface with possible binding sites and a particular gas in the headspace above the surface, and we come to an equilibrium between adsorption and desorption of the gas particles. There's a pressure P in our system. We'll call these gas particles G. We'll call the total number of sites sigma 0. So this would be the total number of possible binding sites on that surface. We'll call sigma the number of bound sites. So in this case it would be 3. And sigma bar equal to the number of unbound sites. Okay, then of course total number is sigma plus sigma bar. We can define a fraction of occupied sites as y equals sigma over sigma plus sigma bar. In the literature, you'll often find y as theta, capital theta, or sometimes small theta. We're going to use y here. Okay, so let's set up this equilibrium. So we have the gas plus a site. So we'll call a particular site S, and the gas particles G is in equilibrium, chemical equilibrium, with GS. Okay, so GS is going to be this unit, the site with the gas particle adsorbed to it. Okay, well, we can write the expression for K. K is just products over reactants. So this is going to be sigma over P, pressure of the gas, times sigma bar. And so let's make sense of that. So sigma, number of bound sites, so that's going to be this. This side is gas and unbound site. Okay, so we have products, which is just this, over reactants, and so since G is a gas, then we're going to talk in terms of pressure. Later we'll see this, like when we're talking about drugs binding, we'll talk about it in terms of concentration. But here the natural language for the equilibrium is in pressure of the gas, and then the unoccupied site for the S here. So that's our K. Now let's try to express Y in terms of K and the pressure. So can we get rid of the sites? And the reason for that is pressure is a very easy thing to measure, and this number of sites is a difficult thing to measure. We can get estimates based on the structure and the morphology and measurements that we might take of that, but it'd be nice if we can get the expression to not involve having to count the number of sites and unbound sites. So let's re-express our K as our K equation as sigma equals K P sigma bar, and that's just rearranging this equation. And let's write our equation like this. I'm going to just switch the order there. So then I can write Kp sigma bar over sigma bar plus Kp sigma bar. And the nice thing here, there's a sigma bar in each term. This cancels, and this gives y equals Kp over 1 plus Kp. And this is the Langmuir isotherm. So if you Google Langmuir isotherm, this is what this is the equation you would get, or Langmuir equation. Now, let's plot this equation. So y is going to be a fraction, right? So y should run from 0 to 1. And we'll plot this as a function of p. Okay, now what we see is that if p is 0, then we get 0. But if p becomes very large, right, we get Kp plus 1 being essentially Kp. And so this approaches Kp over Kp, which is 1. So this will asymptotically approach 1. Right? And this is characteristic of a saturation. So if we think about it, if we make the pressure so big, eventually we're going to fill all those sites, right? And we're going to saturate the system at the full number of sites. And the curve then is just this growth up to that saturation. Now, let's think about this equilibrium a little bit. Again, as we increase the pressure, right, we're going to shift the equilibrium this way. Right? We see this phenomena kind of connecting to our isotherm over here. So that pushes us this way. If we reduce the pressure, then by Le Chatelier's principle, we're going to shift this way. And that corresponds to being down here on the isotherm. Another thing we should note about K is the unit. These are unitless, I guess they have the same unit number of sites. So this is unitless. So the units on K are 1 over pressure. Okay, and so that leads us to how do we characterize this curve? Because it's asymptotic, we don't like to talk about the fully saturated case because we can't really pinpoint a quantitative value here for a comparison amongst different types of gases or different types of surfaces. And likewise, we don't want to consider 0. So what's typically done is we consider the halfway point. And we'll call this special pressure P1/2. And so we can characterize a Langmuir isotherm by the pressure at which we get half of the sites occupied. So let's derive an expression for that. So we'll take our Langmuir isotherm, set y equal to 1/2. I have to be careful to label my pressure so that we're talking about this particular pressure point. So let's say solve this. So we have 1 plus kp 1/2 equals 2 kp 1/2. And so we get kp 1/2 equals 1. So I just brought this kp over here. So that subtracts a kp. So I have 1 equals kp, and then I just switch the order here. And solve for p 1/2. It's 1 over k. So this point right here is 1 over k. All right, well, let's apply this to a question of how do we compare, say, 2 different gases or 2 different surfaces, some different system in terms of the Langmuir isotherm. So let's say I have 2 systems, system A and system B, and we want to compare which has better adsorption. So we take the point at 1/2 and we trace this over. Okay. This is going to be P, this is going to be 1 over Ka. And this is going to be 1 over Kb. So we see here that Ka must be greater than Kb. So when we consider our expression, gas A, say these are 2 different gases but the same surface. Let's just do that. Plus S we see that gas A adsorbs better to the surface. It has a larger equilibrium constant. Okay. What about temperature? And we're not going to say much here in terms of a derivation, but we're just going to pull from kinetic theory of gases. So we won't talk about that much in this video series, but of course we'll have other videos with where we get into the kinetic theory of gases. And it turns out that for this type of a system, the equilibrium constant is proportional to 1 over the square root of RT. So K goes down as T goes up. And so if we think about that, I think that makes some sense. As we heat up the system, it's easier for the molecules to desorb from the surface. And so for similar conditions except a change in temperature, we would expect the system to be shifted shift to more desorption as we raise temperature and more adsorption as we lower temperature. So we can represent this graphically again with the isotherms. So we have 2 different temperatures. Let's find that halfway point. So here we see K1 is greater than K2, and because of this inverse relationship that says K2 or T2 is greater than T1. And so we see a shifting of that Langmuir isotherm as we increase the temperature. All right, we'll get into, as we progress through this, we're going to get into some more complicated models, more sophisticated models for absorption that depend on like different surface sites, whether the binding is cooperative, whether the adsorption can occur in multiple layers. So we're going to nuance some of these ideas. We're also going to see a number of applications. Next time, in the next video, one of those will be simply to recast this in terms of concentrations of, say, drugs or neurotransmitters. So we'll write this in terms of concentration versus pressure, along with some other applications.